In this lesson, we are going to focus on the difference between the addition rule and the multiplication rule. And these are two of the most used rules in probability. In the previous section, we talked about the difference between being independent versus dependent, and mutually exclusive versus not mutually exclusive. And now we're going to really focus on using these rules and identifying whether we have those special cases or not, and practice some examples. So let's do a quick review of the rules. When you are trying to find the probability of an or statement, and you have, for example, the probability of an event A happening or an event B happening, and the notation would look like this: probability of A or B. The general rule is that you want to add the probability of A plus the probability of B, and then you would subtract the probability of A and B. So this is the general rule. We do have the special case when you have two events that are mutually exclusive. And mutually exclusive, just as a reminder, it just means that A and B are not going to happen at the same time. So if you have something that's mutually exclusive, that means that the probability of A and B happening is going to be 0. So in the case that you have something that's mutually exclusive, your probability of finding A or B is just going to be the probability of A plus the probability of B, because in the event that it's mutually exclusive, this is going to be equal to 0. And I'll abbreviate ME for mutually exclusive. So that's a special case with the mutually exclusive. Okay, now for the multiplication rule, that's when we're trying to find the probability of A and B. And in general, we would say that the probability of A and B could be one of two things. It just depends on the information that's given to you. It could be the probability of A times the probability of B given that A has occurred, or you can reverse it and write it as the probability of B times the probability of A given that B has happened. So this is our general rule. Now, in the special case where you have A and B as independent events, as we discussed in the previous section, then we would know that the probability of B would be equal to the probability of B given that A has happened, or vice versa. We would also have the probability of A would be the same thing as the probability of A given that B has happened. In other words, the probability of B is not going to be affected by event A, and the probability of event A is not going to be affected by event B. So this would be the special case if they were independent. Now, if they were independent and you have that these are equivalent, then you would have where the probability of A and B is just the probability of A times the probability of B. All right, so let's go through some examples and practice this. If you forget the meaning of mutually exclusive or independent versus dependent events, I would suggest that you go back to section 3.2 and do a quick review where I go into that in more detail. Okay, so in the first example, it says Carlos plays college soccer and he makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. A is going to be labeled as the event that Carlos is successful on his first attempt, meaning he gets a score the first time. So that probability would be 0.65. B is going to be the event that Carlos is successful on the second attempt, meaning on the second try he gets a score. And that probability is going to be given that he has made the goal on the first try. So let's label the notation here. So the probability that he gets a score on the first attempt is 0.65. But they're stating that the probability that he gets a score on the second attempt, assuming that he made a score on the first attempt, is 0.9. So the notation for that would be the probability that he gets a score on the second attempt, that's event B, given that he has got a score on the first attempt. So that's the notation we're going to use, and that's given to us in the problem, which is 0.90. We're going to use this information to answer the following questions. So part A says, what is the probability that he makes both goals? So this means we're trying to find the probability that he gets a score on the first attempt and a score on the second attempt. Now, in general, if we look back up here, the rule for and is we multiply, and we would take the probability of A, and we would take the probability of A times the probability of B, given that A has happened. There's other ways that you can write it too, but based on the information that we're given, this is what we're going to use. If we look back up here, we can write it this way, or we can write it this way, where I just highlighted under blue. Either way, those will be equivalent. However, because we were given the probability of B given A, I chose to use this first formula because this is the information that we have. Okay, so we know that the probability of A is 0.65, and we know that the probability of B given A is 0.90. So when I multiply these together, 0.65 times 0.90, I'm going to get 0.585. So the probability that he is going to make a goal the first time and the second time is about 58.5%. Okay, part B in this question, it says, what is the probability that Carlos makes either the first goal or the second goal? So now we're using an or statement. We're finding the probability of A or B. And if we look back up at our general statements, we want to add when we have an or statement. So I'm looking at this right here that I just highlighted blue. I want to find the probability of A plus the probability of B. And then I want to subtract the probability of A and B. And we know that our general rule is that when we find the probability of an or statement, we want to find the probability of A plus the probability of B, and then subtract the probability of A and B. Now it says in the problem, in general, there's a 65% chance that he's going to score. So on each individual attempt. So for both probability of A and probability of B, that's going to be 0.65 on any individual attempt. Now we have to subtract off the probability that he would make it for both attempts to subtract off any overlap. So we found in part A that the probability of him getting a goal, we found that the probability of him getting a goal both times is 0.585. So I'm going to subtract here 0.585. Now, when I take 0.65 plus 0.65 and then I subtract the 0.585, that's going to give me a 0.715. So there's about a 71.5% chance that he would score on one or the other. Part C says, are A and B independent? Now, in order for two events to be independent, we would know that the probability of A is going to be equal to the probability of A given that B has happened, or we can write it the other way. The probability of B would be the same as the probability of B given that A has happened. Now, if we look at this, the probability of B is 0.65, and the probability of B given that A has happened is 0.90, and these are not equivalent. So we would say no, they are not independent. If they were independent, these two values would be the same. Are A and B mutually exclusive? We know that if two events are mutually exclusive, the probability of A and B happening must be 0, meaning they can't happen at the same time. And we showed in part A that the probability of A and B was equal to 0.585. Because the probability of A and B is not equal to 0, I would say these events are not mutually exclusive. In the next example, it says a community swim team has 150 members. 75 of the members are advanced swimmers. 47 of the members are intermediate swimmers. The remainder are novice swimmers. And it says 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week, and 10 of the novice swimmers practice 4 times a week. Suppose one member of the swim team is chosen randomly. And then we have to use that information to answer all of these questions below. In a problem like this, when they're throwing a lot of different numbers at you, at least this helps me. I think it really, really helps to organize the information that's given to you in a table. By organizing it that way, it makes it a little bit more clear on what information is given to you and what is still needed, and if there's anything additional that you can figure out from all the information that's given to you. So I'm going to make a chart to organize this data. I'm going to label N for novice, I for intermediate, and A for advanced. And then I'm going to label 4x for 4 times a week. And then I'll put N for, I guess I can label it that way, for not practicing 4 times a week. So the 4x is for practicing 4 times a week, and the N4 is for not practicing 4 times a week. Now, the information that's given to us in the problem says there is a total of everybody in this group that is 150. So I'm going to label that down here in the ultimate total column. Now, if we go through and we find all the information that's given step by step, then we can enter it into this table. It says 75 of the members are advanced swimmers. So of all of these 150 swimmers, there's 75 that are advanced. So I'm going to put 75 in the advanced column at the bottom for the total. It says 47 are intermediate. So I'll put 47 here. And then it also says the remainder are novice. Since we know that it has to total to 150, so I know 47 plus 75 plus however many novice there are should be 150. I can put down there that I know that this should be 28 for the novice. So there's information that wasn't given to us, but by organizing the data, we could quickly figure it out. Okay, now they go on to explain how many times a week some of these people are working out. 40 of the advanced swimmers practice 4 times a week. So in the advanced column with the 4 times a week, I'm going to put 40. Then let's see, it goes on to say 10 of the novice swimmers practice 4 times a week. So this would be 10, which would make the people in the novice group that do not practice 4 times a week, that should be 18. And then it also says 30 of the intermediate swimmers practice 4 times a week. So that would be 30 4 times row in the intermediate column, which then tells me that there are 17 of the intermediate players that do not work out 4 times a week. And then we can go across and actually total the rest of these as well. But in any case, I know that it should total either this way or this way. I should have a total of 150. And even though that took an extra couple minutes to fill out that table, it actually does make answering these questions so much easier. So in part A, it says, what is the probability that a member is a novice swimmer? So out of all of these 150 people, there's 28 novice swimmers. So I would say 28 out of 150. And then we can approximate that as a decimal as 0.1867. Part B says, what is the probability that a member practices 4 times a week? So if I look at all the people that practice 4 times a week, whether they're novice, intermediate, or advanced, there's a total of 80 of those. So that would be 80 out of the 150, and we can approximate that as a decimal as 0.5333. Okay, the next question, what is the probability that a member is an advanced swimmer and practices 4 times a week? Well, if the person is an advanced swimmer and practices 4 times a week, then it would have to meet both of those conditions, which means we're looking at this group right here, the 40, that's in the advanced column and in the 4 times a week. So that would be 40 out of 150, which would be about, if we put that in decimal format, that would be 0.2667. Okay, now part D says, what is the probability that a member is an advanced swimmer and an intermediate swimmer? So the probability that a person is advanced and intermediate is going to be 0. They're in one column or the other, right? Here's all the intermediate people and here's all the advanced people. They're in one column or the other. There's not going to be any overlap where they could be both at the same time. And because the probability of being advanced and intermediate probability is equal to 0, then we know that these two events, A and I, are mutually exclusive. And then that goes into answering the last part of that question. Are being an advanced swimmer and an intermediate swimmer mutually exclusive? So we kind of answered both questions at the same time there. Okay, part E, it says, are being a novice swimmer and practicing 4 times a week independent events? Remember, in order for 2 events to be independent, that means their probability of one event doesn't affect the probability of the second event happening. So we would say that the probability of being a novice swimmer would have to be equal to the probability of being a novice swimmer given practicing 4 times a week. Those would have to be the same if they were independent, or the other way around, where practicing 4 times a week, that probability would have to be the same as practicing 4 times a week given that you're a novice swimmer. So these would have to be equivalent. And if we look at the chart above, that probability would be 28 out of 150. We calculated that in part A, which is 0.1867. Now, if we find the probability of being a novice swimmer who practices 4 times a week, then if we look at just the people that practice 4 times a week, that would be 10 out of 80, which is 0.125. These are not equivalent. Because those are not equivalent, these are not independent events. In the next example, it says, Felicity attends Modesto JC in Modesto, California. The probability that Felicity enrolls in a math class is 0.2, and the probability that she enrolls in a speech class is 0.65. The probability that she enrolls in a math class, given that she enrolled in a speech class, is 0.25. We're going to let M be the event that she signs up for a math class. S is the event that she signs up for a speech class. And then, of course, MS is the event that she signs up for a math class, given that she has signed up for a speech class. So let's write down the probabilities that were given to us. The probability of her taking a math class was given as 0.2. The probability that she took a speech class was 0.65. And then the probability that she took a math class, given that she already signed up for a speech class, was 0.25. So in part A, it says, what is the probability that Felicity enrolls in math and speech? So we want to find the probability of M and S. And the general rule for finding an and statement is multiplication, and we would use the probability of the first event times the probability of the second event, given that the first event already happened. Okay, though that's one way we could do it. The other way, if we switch the letters around, we could do this as well. Now, these two should be the same. However, we do not have enough information to use this first one, so we're going to use the second one. We do know the probability of her signing up for a speech class. That's 0.65. We do know the probability of her taking a math class, given that she signed up for a speech class, and that's 0.25. When we multiply those together, we get 0.1625. Okay, part B says, what is the probability that Felicity enrolls in a math or a speech class? So we're going to find the probability of M or S. The general rule for this is to add the probability of the first event to the probability of the second event, and then subtract any overlap, if there is overlap. So that would be the probability that M and S happens at the same time. And we just found that value in part A, so we know that that does happen. That value is 0.1625. So now we just have to add the probability of M and the probability of S. So that's 0.2 plus 0.65, and then I subtract 0.1625, and that would give me 0.6875. So the probability of her signing up for one or the other is 0.6875. Now, part C says, are the events M and S independent? So we want to check to see if the probability of M given S is the same as the probability of M. Well, we know because it was given to us up in the beginning that the probability of M given S is 0.25. And we know that the probability of M is 0.2. Because these are not equivalent, they are not independent. In order for these two events to be independent, this must be a true statement. In other words, the probability of one event is not going to affect the probability of the second event. And that's just not the case in this part C. Okay, part D says, are M and S mutually exclusive? In order for M and S to be mutually exclusive, they cannot happen at the same time. And so in order for that to happen, the probability of M and S, it has to be 0. But in this case, we found in part A that is not 0. We found that the probability of M and S was 0.1625, which means since it's not 0, it is not mutually exclusive. Okay, in this next example, we're going to use the information that's in this example to answer the questions on the next page as well. And the example reads, studies show that about 1 woman in 7, which is approximately 14.3%, who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative about 2% of the time. Also suppose that in the general population of women, the test for breast cancer is negative about 85% of the time. Now, this is important when it says in the general population because it's not conditional. We're not making another assumption, okay? We're going to let B represent the event that a woman develops breast cancer. We're going to let N be the event where there's a negative test. And then we're going to assume that we're going to pick one woman at random at a time and answer the following questions. Now, because we're letting B be the event that a woman develops breast cancer, we're going to write the probability of B is 14.3%, which is given in the first sentence of the problem. But we're going to write it as a decimal. We're going to write 0.143. The probability that a woman tests negative, given that she actually does have breast cancer, would be written like this. It's conditional probability, and we said that that happened 2% of the time, and we'll write it as a decimal as 0.02. And then in general, it says, so that means it's not a conditional probability. We're taking this out of the general population. We're not looking at any subgroups here. It says that the negative tests happen about 85% of the time. So we're going to write the probability of a negative test is 0.85. We'll use this information that's given to us along with the notation to answer the rest of the questions. So part A says, what is the probability that the woman develops breast cancer? And then what is the probability that a woman tests negative? So we already actually wrote that up top when we were writing our notation. The probability of a woman developing breast cancer, we said was 0.143. And then the second part of that, where it says, what's the probability that a woman tests negative? That's the probability of N, the event that she tests negative, and that's 0.85. Part B says, given that a woman has breast cancer, what is the probability that she tests negative? So this is the conditional probability. We're taking it out of the subgroup of the women that actually do have breast cancer. We're making that assumption. So we want to find the probability of the women that do have breast cancer that she tests negative. And we said that that happened 2% of the time, and as a decimal, we would write it as 0.02. Part C says, what is the probability that a woman has breast cancer and tests negative? So that's the probability of having breast cancer and testing negative. And with the and statement, we want to use the multiplication rule. And so there are two options for that. We could write the probability of B times the probability of N given B, or we could write the probability of N times the probability of B given N. Now, we could use either one of these, but this first expression is what we have the information for. So I'm going to use that first expression. We know the probability of B, that is 0.143. We know the probability of N given B, that was 0.02. And so when we multiply that together, we can find the probability of having breast cancer and testing negative out of the general population. That would be 0.0029. Okay, part D says, what is the probability that a woman has breast cancer or test negative? So we have the probability of B or N now. And our general equation for that is that we use addition. We take the probability of each event separately and then subtract off any overlap that we have. And in this case, the overlap would be the case that the person has breast cancer and test negative. Now, we found in the previous example in part C what that value is. We found that that was 0.0029, so I'll write that in there. We know the probability of B, that's 0.143. And I know the probability of N, that's 0.85. When I add all of that together on the calculator, we will get 0.9901. Okay, part E says, are having breast cancer and testing negative independent events? In order for two events to be independent, we have to have the probability of B as being the probability of B given that N has happened, or we can write it the other way. The probability of N has to be equivalent to the probability of N given that B has happened. These have to be true. Now, if this is true, then it's independent. Because we have these values already calculated in previous parts, we know that this is not true. So we know that these are dependent events. That is because we know the probability of N is equal to 0.85, and we also know that the probability of not testing positive to test negative given that the person has breast cancer is 0.02. These are not equivalent. So because of that, we know that these are dependent events. Okay, part F. It says, are having breast cancer and testing negative mutually exclusive? In order for two events to be mutually exclusive, we know that the probability of those two events happening together has to be 0. If they're mutually exclusive, that means they can't happen at the same time. So in this case, since we're talking about having breast cancer and testing negative, we're looking to see if that probability is equal to 0. If it is, then it's mutually exclusive. Well, we know that that's not the case because we found that the probability of B and N in one of the previous examples was 0.0029. Because that is not equivalent to 0, we would say these events are not mutually exclusive. In these last few examples, it's basically a continuation of the previous example, but in these parts of the question, we're going to really focus on the complements and how to use the complements to answer more probability questions. So I just carried down the previous information that we're going to reuse. And so in part A, it says, given that a woman develops breast cancer, what is the probability that she does test positive? So we know that the probability that someone tests negative, given that they have breast cancer, we know that that is a 0.02 chance. So what we need to do, if we want to figure out the complement of that, what is the probability that someone tests positive given that they have breast cancer? That's the opposite of what we have here. So that's the complement, which would be 1 minus the probability that someone tests negative and has breast cancer. And we could also write it like this using the notation. We can write the probability that someone tests positive given, so the P is for the positive, given that they have breast cancer. So we would just take the complement of what we already know, which is the 0.02. So when I take 1 minus 0.02, that gives me 0.98. Okay, part B, it says, what is the probability that a woman develops breast cancer and tests positive? So we want to find the probability. Now this isn't the conditional probability. This is the probability of these two things happening together out of the general population. So this would be the probability of B and P. And when we have and statements, we want to use the multiplication rule. So we want to use the probability of B times the probability of P given that we have B, or we want to write the probability of P times the probability of B given P. Now we can use any one of these, but we have the information for this statement. So this is what I'm going to use. I know that the probability of B is 0.143. I know the probability of P given B is 0.98. And so when I multiply those together, I'm going to get 0.1401. Part C says, what is the probability that a woman does not develop breast cancer? So that is the complement of the event B. We could also write it like this. It just depends on what book you're using. I think our book uses the prime notation, but either one, it means the same thing. So we know that the probability of B is that she has breast cancer. So let's write down that. That would be 0.143. So the complement is going to be 1 minus that. So I'm going to take 1 minus the probability of B, which would be 1 minus 0.143. And so that's going to give me 0.857 when I subtract. Okay, part D, what is the probability that a woman tests positive for breast cancer? So we're trying to find the probability. We know that the probability of someone testing negative, that was 0.85. If they test positive, then that's the same thing as the complement of testing negative. So we're just going to take 1 minus the probability of testing negative, which would be 1 minus 0.85, and we would get 0.15.